2.4, the chain rule. We started this last time. To remind you where we were, we had encountered this rule, and we had had sort of a mnemonic description or a descriptive language surrounding it. Said that what we're going to do when we do a chain rule is we're going to take the derivative of the outside, and we're going to multiply it by the derivative of the inside. Okay? And we had done one example that looks like this. We talked about the fact that what I've highlighted in orange is what's inside, and the power function is what's on the outside. So dealing with the power function meant that I pulled the 5 down, and I decreased the power by 1. And the orange part inside still stays the same. But then after I do that derivative of the outside piece, then I multiply that by the derivative of the orange piece, the derivative of the inside. If there's any cleaning up I can do, I do that. Oftentimes there's not, and so we don't have to do a whole lot. This one there wasn't a whole lot of cleaning up to do. A little bit of multiplication and that's it. But again, on the quiz on Friday, you could actually stop without doing any of the cleanup multiplication, and I would encourage you to do so. So let's try a few more that look a little different as we go along the way. If you take a look at this one, it does not look like it's a chain rule. And in fact, it could be done with the quotient rule, and that would be okay. Wouldn't be anything wrong with that. It's not really a quotient because the numerator is just a constant. Do you see that? Most of our quotient rules that we were dealing with before, they had variable components in the numerator and variable components in the denominator, and this one doesn't really have that. So while it can be done with the quotient rule, that's not the most natural way really to do this problem. It's actually more natural to do a chain rule. So how do I do that? Well, a moment ago on the quiz that we just looked at, I talked about the fact that we don't just move the 3 up to the numerator, right? The 3 didn't have a power. Well, there is a caveat to that. If you take everything that's in the denominator, put parentheses about it, you can move all of it up at once, and you can do it like this. So I have my x squared plus 3x minus 1, and I can make all of it to the power -1. So I take it like a group, shift everything up, and give it a negative exponent. And if I do that, the thing is that it actually ends up looking a lot like the first problem that we did last time, right? I have an inside function, and I'll highlight. And then I have an outside function that's a power. And I can do very much the same thing as what I did on the last problem. So this is g prime of x. Okay, so the derivative of the outside, the part that I've marked in red. What do I do when I have a power rule? What does it say I should do? Bring the exponent down. Ignore the inside for the moment. What will the new exponent be? -2. Yeah, -1 minus 1, so -2, right? Good. So this is actually the power rules. This is the outside derivative. And the part inside will stay the same. So the part that was already here in blue will stay exactly as it is. It doesn't change. There's this tendency to sort of manipulate them both at the same time, and you don't. You manipulate one piece at a time while holding the other piece constant. So I held the inside constant and I manipulated the outside. And then I'm going to multiply by the derivative of what's inside. So what is the derivative of x squared plus 3x minus 1? 2x plus 3. You got it. And on Friday, that's where you leave it on the quiz. You don't do anything else. On your homework, on WebAssign, on tests and things in the future. We are going to clean it up, and we are right now. But this is where you would stop on Friday morning. So what would we need to do? Well, we need to have it look like it began. It needs to look like this form. So this form didn't have negative exponents. I did that on purpose in order to make the algebra and the calculus easier to work with. But I can actually undo that just as easily. I take the part that's written to the power 2, and I write it in the denominator with the power 2. So it's x squared plus 3x plus minus 1 squared. So that's easy enough, right? Just move it down just like I would x to the -2. I'd move down. All of it moves down. And then I've got a negative here, and I've got a 2x plus 3 at the end. So I've got this -1 and this 2x plus 3. And I can combine those to give me a -2x minus 3 on top. Is that right? So just like when we were doing product rules and quotient rules and simple, the basic simple rules, sometimes a little bit of algebra manipulation at the beginning is helpful in order to use a rule in an easier way. It's about to get harder really quick. Yeah, problem number 3 is really different. And the reason it is because the first two examples that I did were chain rule problems, and that's just what they were, just chain rules. This one is a chain rule and a quotient rule. Yeah, I know. I mean, like, we're going to combine them, and like so fast. Like problem number 3, come on, give me a break, right? Yeah, we're going to combine these really quickly. So a few things here to notice. You see that square root. We've seen square roots before. So when we deal with the square root, we've got a power of 1/2. And there's a couple of different ways to do this. I'm going to show you one fully fleshed out. And then I'm going to remind you that there's another way we could have rewritten this and think about, like, just verbally what we could have done instead. Okay? So when I talked about the fact that my gateway solutions online are unique, like there's one solution, but there's sometimes more options, this would be one of those problems that has two completely different looking answers at the end, and they're both right. All right? I shouldn't say in the end. After you clean them up, they look the same, but the intermediate step of actually taking the derivative looks different. So one way to do this is to simply write everything that's underneath the radical to the power 1/2. So I have 3t squared minus 2 over 2t plus 3, and it's all raised to the power 1/2. Okay? So this is one way to do the problem, and this is the way we're going to actually do this particular problem. And then I'll show you another way you could have thought of it. This looks a lot like the last two problems that we did. I've got something, it's messier, but I've got something in here, and it's raised to a power. It's a power rule, right? So what does the power rule say I do with that 1/2? Bring it down. And then what do I do with power? I subtract 1. 1/2 minus 1 is negative 1/2. And then the part that I highlighted in blue stays the same. So 3t squared minus 2 over 2t plus 3. That's the derivative of the outside. It's just a power rule. Where the complication comes is that the derivative of the inside here is actually not a simple rule. It's a quotient rule because I got a quotient, right? So I'm going to multiply this with the quotient rule. So the quotient rule, you guys have finished your web-assigned homework on this, so hopefully you've done quite a few of these and you're remembering it fairly well right now. It says I take the denominator and I multiply it by the derivative of the numerator. So what is the derivative of the numerator? What was it? I'm sorry? 6t, yes. My screen's just not big enough to see everything at once. Thank you. And then there's subtraction. Quotient rules always have subtraction, and then we flip the order. Now we do the numerator, which was 3t squared minus 2, and the derivative of the denominator. And what's the derivative of the denominator? 2. And it's written over the denominator squared, so 2t plus 3 squared. Okay, now for Friday, you're done. And everybody said amen, right? Because what you're going to like what we're doing, you're not going to like what we're going to do next because we've got to clean this thing up and it's going to be messy. It is, right? It just is. But for Friday, you stop right here, all right? So that none of the messy actually makes it wrong. So let's start cleaning this up. And I want to deal with the part in blue for the moment. Let's just kind of hold off on that and let's clean up the other piece. So this is, well, actually, I'll deal with it a little bit. Negative exponents, if you'll remember, they move things to denominators, but since this is a fraction, a negative exponent equivalently would just do the reciprocal. Do you guys remember that fact from, I don't know, somewhere in middle school, early high school? So I could actually flip this over, 2t plus 3 on top, and 3t squared minus 2 on bottom, and it's power 1/2. Okay, so it just flips the fraction, and I make it a power 1/2 instead. We'll come back to that and do a little bit more with that in a minute, but for the moment, let's just hold off. We'll clean this up. So this is 2t times 6t would be 12t squared. 3 times 6t would be 18t. And then I have this negative and this 2, so negative 2 is distributing through, so I have got negative 6t squared and positive 4. All over 2t plus 3 squared. Okay. Some of the pieces in that numerator simplify. So I've got, I'll come back to the first part in a minute. I've got 12t squared and I've got negative 6t, so that's 6t squared. And then I've got 18t and 4. And then in the denominator, I have 2t plus 3 squared. Over here, I've got this 1/2 in front. The power 1/2 on the fraction means that I could put the 1/2 on the numerator and the 1/2 on the denominator. That's a property of exponents as well. So instead of writing it all like it's written, I could write it as 2t plus 3 to the 1/2 over 3t squared minus 2 to the 1/2. Do you remember that property of exponents? Everybody's staring at me like I'm speaking either something that's really like obvious or like you're not sure what I'm saying. I'm not quite sure how to read you guys today. Maybe you're just tired. I don't know. Is everybody okay so far? Does it look all right? You can see where the pieces came from. Yeah? Okay. That's the important part. Here's something I want to show you. Well, a couple things. First, the part that's the trinomial in the second numerator, right over here, it doesn't cancel with anything in the denominator. And the reason that I know that it can't is because that 4 at the end, if it factors either into 4 and 1 or 2 and 2. And that won't give me the 3 right here, right? So it won't factor in such a way that it will reduce with the denominator. Now, it might factor in such a way that it could reduce with this denominator. That's possible. Agreed? Because that has a 2 at the end. So we might need to consider whether or not this factors in a moment, but it wouldn't need to within its own fraction piece itself. Now, if you'll remember as well, taking a look here, this piece and this piece, they match in the sense that they're the same factor. They both say 2t plus 3. Yes? One of them is 2t plus 3 to the 1/2, and the other one's 2t plus 3 to the 3rd. And they're division, right? Like one of them is really divided by the other piece. So properties of exponents, this one's a huge properties of exponents problem, says that I can subtract those exponents, right? I can do the 1/2 that's in the numerator minus the 2 that's in the denominator. Or you can think about what's really happening there is that I have a square root of one of them, and in the denominator I have it written twice, right? That's what squared means, it's there twice. I think that's a little bit trickier to think about. The properties of exponents are easier to work with, I believe. So over here at the beginning, I still have my 1/2, which I'll have to deal with in a minute. And I have that numerator that's in blue, so I'm going to rewrite it right now. So that's 6t squared plus 18t plus 4. I still have the same denominator that I originally had in the first fraction. So 3t squared minus 2 to the 1/2, sorry. And then instead in the denominator now, I have a 2t plus 3. And I have it to the power 3/2. And where did I get 3/2? Well, what I did is the numerator was 1/2 minus the 2 that's in the denominator, those exponents. 1/2 minus 2 is actually, well, I'll just put it underneath, negative 3/2. And negative 3/2 would be in the numerator, moved to the denominator would be positive 3/2. That's the algebra that's going on there. Okay? So we have 3/2 in the denominator. Take a look right here. This 2 will cancel with some of these numbers here. In fact, all of them, right? Yeah? So we can reduce that piece as well. And I've run out of space, so let me shrink something up here. I didn't quite get everything shrunk quite right. There we go. I don't think that's where that squared goes. Where did that square go? Here? There. Okay. So this one with each of those will reduce by a factor of 2. So now I have 3t squared plus 9t plus 2 over 3t squared minus 2 to the 1/2 times 2t plus 3 to the 3/2. All right. That numerator is not going to factor, at least not into anything reducible in the denominator. We mentioned before that this 2 stands a chance because there's a 2 here, and that's true. And this 3 stands a chance because there's a 3 here. But do you know why it's not going to factor by looking at it? It can't make a 9. That's true. That's one way to think about it. There's another way, too. What's that? It already has a squared. That's part of it as well. Yep, there's a square in here. Good noticing. And there's one more piece that makes it for sure when you look at it. Another third way that you could look at it. There's a negative. Yeah, there's a negative 2 right here. And all these would be positive because the numerator's got all positive pieces. So any of those reasons would be a trigger for you to say, I don't need to keep going. It doesn't even matter if it factors any further, so I don't have to try. Okay? So this is our answer to the problem. As ugly as it looks. All right, so I'm not going to do out completely the other way of doing this problem, but I want you to recognize there is another option. What we could have done is we could have done 3t squared minus 2 and written that to the 1/2, right? Distribute the 1/2 power, and done 2t plus 3 to the 1/2. If I distribute it like that at the beginning, instead of starting with the chain rule as my outside function, I would actually start with a quotient rule as my outside function. And each time I take the derivative of the numerator or the derivative of the denominator within the quotient rule, I'd be using a chain rule. Okay? So that's another way of doing the problem. If you do the problem that way, you do all the steps properly and so forth and clean it up in the end, it will work out to being the same thing we already got. But the intermediate kind of steps along the way look quite different because the process is done in sort of the reversed order. Okay, but that is another way of doing that particular problem. Okay, you ready for doing something a little bit easier, like way easier, like you're just not even going to believe how much easier? Of course you are. It's got trig involved, but I'm telling you, not even close in terms of ease of doing business here. All right, we've got sine of pi x. Do you see an inside function? Because there's definitely no parentheses. Doesn't kind of look like it, right? But there are some understood parentheses here. Where are the parentheses understood to be? Yeah, around the pi x. So I would encourage you as you're starting this process, especially if you haven't had any calculus classes before and are having difficulty identifying inside and outside, to ask yourself that question. Are there some understood parentheses that are here? And if there are, put them in. Makes it a little bit easier to identify. So I have the advantage of colors, so I like to use my colors to help me. So the part that I've highlighted in blue is my inside function. It's inside a set of parentheses. So on this function, the outside function is not a power rule. The last 3 problems, or the first 3 problems in this lesson that I did, all of the outside functions were power rules. The outside function here is a trig rule sine. So what is the derivative of sine? It's cosine. And all I need to do is to rewrite the blue part as it is. Pi x. But then I need to multiply by the derivative of pi x. Remember, pi is just a number. I heard the people on the radio yesterday morning, I don't remember if it was Caleb or Erwan, we switched back and forth, talking about useless things that they learned in school, and they talked about the fact that pi was equal to 3.14, and I cringed immediately because it's not, right? They didn't even learn it right. They learned it, but they didn't even learn it right. Right, that's an approximation for it. Okay, pi is not 3.14, but it is a number whose approximation is 3.14. The thing that happens to us when we get into calculus is that it doesn't really look like our other numbers, so we sometimes forget that it's actually a number and we don't treat it that way. It is a number. So what is the derivative of pi times x? It's pi, yeah. Right, what would the derivative of 3x be? 3. So the derivative of pi x is pi. So the only thing to do to clean this up would be to write the pi in front. You can leave the parentheses off from around the pi x if you wish, or you can put them on. It doesn't really matter. And you all breathed a sigh of relief because that was a way easier problem than the last one, right? So not all chain rule problems are super ugly and messy, but some of them are. Let's try another one with a little bit of trig. We have 5 cosine squared 3t. So there's several things that you need to be aware of in this problem. The first is the fact that this square right here is written where we normally write a square for a trig function. That's fine, except that for the purposes of what we're doing, it's not really in a place that's helpful for identifying what to do next. So it might be very helpful to instead write that this is the cosine of 3t squared like this, right? It's the cosine of everything that's being squared. So let's just write everything in parentheses with a square on the outside. Second thing to identify is that just like on the previous problem where I had pi x as an angle inside of sine, I have the 3t inside of cosine. I think I'll just do it in black actually. So in this problem, what makes it very unique compared to what we've done so far is that there's embedded parentheses. I have a function that's inside of cosine, and I have a function that's inside of the power function 2, with the power 2, right? So this is two inside functions. This is going to involve using the chain rule twice because there's two embedded functions, okay? We don't do it any differently. We just have to be aware that the process will have 3 steps to it instead of just 2 steps. So the 5 at the beginning doesn't really get affected, right? Like it's just a constant multiplier. So let's identify first that this is the inside function in blue and the outside is the power 2. So dealing with the power of 2, what do I do?
Bring it down.
Bring it down with the 5 in front, so that's going to make it 10. And then I make it a power of 1. I'm going to write it for now. If you don't want to write it, that's fine. I don't care. But it is a power of 1. And then the blue part on the inside stays the same. So inside of this is going to be cosine of 3t. And I'm just going to leave my 3t in parentheses for the moment. Next, we need to look at the actual part that's inside, highlighted in blue. I'm going to box it in purple for the moment. Looking at just the part that's boxed in purple, there is another inside and outside function. The inside function, I'll highlight it a different color. Red. No, I've already used red. How about orange? 3t, okay, is inside, so we're going to just ignore it for the moment, and I want to talk about cosine. Cosine is the outside function of what's in the purple box. What is the derivative of cosine? Negative sine. Actually, let me not even put parentheses. Let me just put that dot like I was doing before. Negative sine. And then what goes inside of it is what originally was inside of it. So what's going to go inside with the orange? 3t. But then I have to multiply by the derivative of the orange piece, which is 3. Okay, so I had 3 different derivative steps. The derivative of the outside, the derivative of the first inside function, and then the derivative of the second inside function because it was embedded the way that it was. Again, on your quiz on Friday, you'd stop right here. You'd be all good to go. For today's, what we're doing, we're going to clean up what we can. You'll notice that you have a 3 and a 10 and a negative, so that's negative 30. And then I have cosine of 3t and sine of 3t. And you can put the 3t's in parentheses if you want to. You can leave them off if you want to. They're understood to be there, so they don't have to actually be visible. Any questions on that? Double inside functions. All right. How is the squared here different than the squared on the last problem? It's only squaring the pi x. It's not actually squaring the cosine, right? It's really important to recognize that because it's an easy mistake to just sort of move on quickly and think that you've got the right one. This square is only squaring the pi x. All right, so part of this is interesting because I actually have 3x involved in the problem, and that's just a simple derivative rule. So you don't have to do anything messy or creative with that. It's boring, super boring. What's the derivative of 3x? 3. So do it and be done. The other part is the more interesting part, right, that it applies to this particular section with chain rule involved. I have an inside and I have an outside function. So we have to be really careful what we have inside versus what we have outside. So if we're looking at, where's my highlighter? If we're looking at the inside function here, all of this, including the 2, the power of 2, is inside of cosine. Does everybody get that? Okay, all of it is. So there's sort of this understood, if you will, set of brackets right here that says all of this is inside. So what's my outside function for this particular portion of the problem? It's the 5 cosine. So what's the derivative of cosine? Negative sine. So this will become positive 5 sine. And the part that's in orange gets rewritten. So pi x squared. That's my orange piece, the inside function. Okay. Then, looking at the pi x squared, you have 2 options. You can treat it like a chain rule if you wish, right? The pi x is raised to a power of 2. That's okay. Or you can distribute the square if you wish. It's pi squared x squared. So do you want to distribute the squared or do you want to treat it like a chain rule? Distribute the squared. That's what Kaylee. Yes? Kaylee says. Okay. I keep wanting, I don't want to say it wrong because then I'm going to stick it in my mind wrong again. Okay, so if we distribute the square here, this is actually pi x, I'm sorry. That's okay to see. Pi squared x squared. Okay, pi squared is a number, right? Somewhere in the vicinity of between 9 and 10, because it's like 3 squared-ish, right? It's a number. So pi squared's its own little guy. But what's the derivative of the x squared? 2x. So out here at the end, I have pi squared, it's a number. And then I have 2x, because the derivative of x squared is 2x. So on this one, it looked like there was a double embedded function, right? A double inside function. And you could do it that way. It wouldn't be wrong. You'd get the same answer in the end, right? I mean, you would. But it's probably a little bit easier to just do a little bit of algebra in the middle of this instead of messing around with the calculus and double embedding the functions. That's right. Sometimes it's easier to do math in your head than your calculator. You guys know that, right? I see kids, I had people, there was one time I had somebody grab their calculator in office and I asked them to do like 9 plus 7, and I'm like, oh my word, no, we can't do that. You should do this in your head, right? Calculator is not necessary. Okay, so let's clean this up, see what pieces we can combine. Obviously, the 3 at the beginning doesn't need any work to it, but here I have a pi squared and 2x and 5, so I can combine all those pieces to give me the 10, and then pi squared, I'm going to put all the numbers together usually, and then x, and then sine. And you can write the sine the same way it was before if you wish, right? Pi x squared. If you'd rather write it as pi squared x squared, you could do that as well. Okay. Either way is fine, doesn't matter. Parentheses or no parentheses, doesn't even matter on that. Okay. The inside of sine is pi squared x squared, or pi x quantity squared. Any questions on that one? All right, the next problem is quite similar. In the directions, I should say, are quite similar. There's one piece of it that's different, so let's take a look at that. It says to evaluate the derivative of the function at the given point, use a graphing utility to verify. So when it's asking you to evaluate at a given point, it means that you're going to do everything you've already done, take the derivative, right? But then you're going to plug the values that it gives you in for x, and eventually we'll have an x and a y we plug things into later on. That's why this book likes to give you the ordered pair, x and y at the same time. So you don't really need the y coordinate for now, but it's there. This problem actually looks a lot like problem number 2, I think it was that we did. Yep. Where the denominator is a variable with some addition and subtraction, and the numerator is just a constant. So we'll do that with the chain rule because, again, it's easier to do the chain rule than to do the quotient rule, generally speaking. So I have x cubed minus 2. Pull it all up to the numerator, and it's to the power negative 1. I don't know why I just wrote negative 2. Negative 1. Okay, so bring it all up to the numerator with a negative 1. Okay, is everybody good so far? Okay, so we're going to take the derivative. What is my inside function? Yep, x cubed minus 2. So that means that the outside part must be the negative 1. So what do I do with the outside portion to get its derivative of the outside? Bring the negative 1 down, so it's going to make it a negative 5. And what will the new exponent be?
-2.
-2. And then the inside stays the same, x cubed minus 2. Now I'm ready to do the derivative of the inside. So what's the derivative of x cubed minus 2? 3x squared. And then that's it, right? Because the 2 parts is 0. Now, technically, nothing in the directions here say you have to clean this up and simplify it before you evaluate it and plug numbers in. So there might be cases where right here you just start plugging numbers in, especially if you're plugging in 0. I mean, zeros are beautiful. They make things disappear. You don't even need to simplify and so forth. This one's not a 0, so I'm going to go ahead and clean it up a little bit just because I think that actually might be the easier way to do the problem. But just recognize that with the directions stated as they are, nothing says that you have to clean this problem up before you plug values in. Okay? So on this one, I have a 3x squared at the end and a -5 at the beginning. So this is -15x squared. And then because the part that's in orange is to a negative power, I can pull it back into the denominator and make it squared to change the exponent, right? To reflect that I've shifted it from the numerator to the denominator. All right, so this is the derivative function, and it wants me to evaluate it at the x value of -2. So we're going to plug -2 in all the places. This is actually going to be finding f prime of -2. So I have -2 squared on top times the -15. And on bottom, I actually have -2 cubed minus the 2 squared. Sometimes the cleanup is just as easy to do in your head. Sometimes you might want to grab your calculator and plug it into the table or into the calculator screen, and that would be fine as well. Either way is fine with me. I don't really care that I see all of the algebra, or not the algebra, the arithmetic written out. This is sufficient to show me that you've plugged the number in and then find out what's next. So we'll just do it in our heads because I think the numbers are small enough to be able to work with okay. -2 squared would be 4 times the -15 in front of it is actually -60, yeah. In the denominator, -2 cubed is -8, minus 2 more would be -10, and then -10 squared would be 100. So this is -60 over 100. Obviously, the zeros at the end can be divided by 10, so they would disappear. So you have -6 over 10, and then 6 and 10 are both divisible by 2, right? So you can divide them both by 2, so you'd get -3 over 5. Okay, -3/5. If you want to write it as a decimal, it's -0.6. That's fine. Doesn't matter because it's terminating. That'll be okay. And we will be done with the problem. You won't be asked to plug anything in on your derivative. Great way on Friday. Okay, it's just the derivatives, nothing else. Oh, it did say to verify with your calculator. Let me remind you how you do that. That's that nderiv feature that it's talking about. So you do nderiv, you plug the original equation in, you tell it to do nderiv at y1, the variable x, and so forth. Are we out of time? No, we have one more problem. Don't go too fast. Did it print off? Number 8? Do you guys have that one? Okay. Sorry, everybody's closing their notebooks up. So yeah, the nderiv is how you would do the part B, if you will, of this particular problem. Okay, last problem. It says to find an equation of a tangent line, okay? So when we're finding the equation of a tangent line, all the steps are the same as the last problem we did. We take the derivative when we evaluate it. And when we do that, remember, it finds us the slope. Once we have the slope and the point that they've given us, we can use either y equals mx plus b or y minus y1 equals m times x minus x1 to find the equation. And then on part B, where it says to use the graphing utility to verify, it means that we graph the original function with the slope line that we just found, the tangent line that we just found, and we verify that, yeah, it looks like that's a tangent line. It's just barely touching the graph. It's not cutting clean through it. So that's what this problem is asking us to do. It's actually a pretty clean one in terms of a chain rule. Everything's inside of a parenthesis, and it's to the power of 2. So we're going to pull the 2 down. Rewrite the part that's orange on the inside, make it to the power 1, right? And then multiply by the derivative on the inside. So 4x cubed will give me 12x squared. And then the plus 3 is, of course, 0. So again, this is actually where you'd stop on Friday, right? For the purposes of what we're doing, we're wanting to evaluate it at the value 1. Well, I don't have any negative exponents. I don't have any fractions going on. I don't really see any reason to clean anything up until I put the number 1 in, right? It said, or sorry, negative 1. So I'm going to plug in the number negative 1. So this is 4 times negative 1 cubed plus 3. It's to the power 1. I don't really need to worry about that. And then I have 12 times negative 1 squared. And I can work through this because there's 1s really nicely. Negative 1 cubed would be negative 1. Times 4 would be negative 4. Plus 3 would be negative 1. So this is 2 times negative 1. And then I have at the end 12 times negative 1 squared. Negative 1 squared is 1. So this is just 12 at the end. So the grand 2 times negative 1 times 12 would be negative 24. Okay, and that's the slope for our line. Yes? Okay, if you want to do y equals mx plus b, y is 1, x is negative 1, m is 24. To find b, you can use the other form of the line too if you wish. 1 equals negative 24 plus b. So b would actually equal, did I get my numbers in the right place? Yeah, I did. Okay. B would equal what? 25.
Wouldn't this one be negative 24?
Yeah, that's my negative extra. I thought that I was supposed to be getting a different answer. So this is positive, and then negative. Thank you. I was looking for the sign error, and I couldn't find it, so I thought, well, maybe there's an error on my note sheet. Thank you. Negative 23. That do it? So my line is y equals m, which is negative 24x, plus b, which is negative 23. And we will grab our calculator really, really quick, and we're going to graph the equation that we just found, that line, and the equation we were originally given at the beginning to start with. Whoops. And I'll do it over here on this screen, because I've run out of space on the other one. It looks kind of like this. This actually touches right there. Something like that. That's the original equation. And then the tangent line that we just found, overlaid on this, looks something like this, but it touches right there. There we go. Looks like a tangent line, right? And I'm probably a little bit off of my scale, of course, and things like that. But that's roughly what your calculator screen should be showing you to verify that you do indeed find a tangent line at x equals, and it's supposed to be at negative 1, 1. Obviously, my scale's messed up, but you have the right idea from my screen. All right, so for Friday, please, please, please practice for the derivative gateway. Remember, you get to take it unlimited time. Well, not completely unlimited, but many, many times. And that's great, and that's good news. But if you take it the first time and you pass it, you get extra credit, and you don't have to spend your time coming and visiting me in my office. So it's bonuses for you, on both ends of that. You do not get to have anything with you except your pencil when you take that gateway. No calculators, no nothing. There's no simplification required. There's really nothing they could help you with, so we just keep them put away, okay? So we'll start on Friday with that, with the derivative gateway. We'll take 30 minutes to do that. At 30-minute mark, or if everybody's done earlier than that, we will move on into our next lesson in 2.5. And web assignment, of course, is also due for 2.4 as well on Friday.